Hi, my name is Stephen Yan, and I'm here to talk to you about the stress-strain relationship for tensile testing. Tensile testing is one of the most fundamental and widely used methods for measuring the mechanical properties of materials. It involves subjecting a test specimen to an increasing tensile load until it reaches its breaking point. By measuring the load and the resulting deformation, we can determine a range of mechanical properties, including the Young's modulus, yield stress, ultimate stress, and the elongation of the material. In this presentation, we'll delve deeper into the stress-strain relationship and explore how it can be used to characterize the mechanical properties of materials. We'll also look at the various stages of the stress-strain curve and what they tell us about the material's behavior. In this experiment, we focused on testing the stress-strain relationship for an aluminum 2024 specimen, which is a common material used in aerospace applications. By using an Ingstrom 5982 load frame unit, we're able to apply a monotonically increasing tensile load to the specimen while collecting various measurements. These measurements included the dimension of the aluminum specimen before and after failure and the stress-strain curve during the loading test, which was measured using the strain gauges and an extensometer. With this experimental background, we can now take a look at the results. First, we collected various measurements, including the dimensions of the specimen before and after testing. Using a vernier caliper, we measured the width and thickness of the specimen before and after it reaches breaking point. The results showed a decrease in both the width and thickness of the specimen after testing, which was caused by the elongation of the material. Specifically, the width was reduced by 0.071 inches, corresponding to a 14.2% decrease, and the thickness was reduced by 0.02 inches, which corresponds to a 23% decrease. This means that the cross-sectional area decreases as we apply the tensile load. Recognizing the changing area is crucial, as we later use this fact to derive the relationship for true engineering stress and strain. One of the most important pieces of data collected during the tensile testing was the stress-strain curve. This curve provides insight into how the material responds to the applied tensile load and can help us understand the material's mechanical properties. The stress-strain curve is plotted as the stress on the y-axis and microstrain on the x-axis. This includes both the extensometer and strain gauge data. The curve shows several important regions and points. The plastic deformation region occurs between 0 and 4,000 microstrain, where the material undergoes significant plastic deformation without experiencing a significant increase in stress. This region corresponds to the initial linear portion of the curve. The yield stress occurs at 6,000 microstrains, which is the point where the material transitions from elastic deformation to plastic deformation. This is an important point because it provides an indication of the material's strength and how much it can deform before it starts to yield. The strength hardening region occurs from 6,000 to 150,000 microstrain, where the curve becomes significantly flatter, meaning the strain increases rapidly as the stress increases. The ultimate stress occurs at 150,000 microstrain, which is the maximum stress of the material can withstand before it starts to fail. Finally, the necking region occurs from 150 to 160,000 microstrain, which is the point where the material starts to narrow and the cross-sectional area decreases rapidly. The end point of this region is also the rupture point, which is the point where the material ultimately fails due to the applied tensile load. From the stress-strain curve shown on the previous slide, we can figure out the Young's modulus of the specimen fairly easily. The Young's modulus is a material property that describes the stiffness or resistance of the material to deformation under stress. It is defined as the ratio of stress to strain in the linear region of the stress-strain curve. In other words, it is the slope of the linear portion of the curve. In our testing, we calculated the Young's modulus of the specimen using the measured data from the stress-strain curve. The equation used to calculate this is as follows, where the sigma represents stress, epsilon represents strain, and E is the Young's modulus. The final calculated value for Young's modulus is 74,179 megapascal, which is very close to the published value of 73,100 megapascal for aluminum 2024. This indicates that our testing was accurate and the specimen behaved as expected under the applied stress. Next, let's look at the true stress and strain data. The true stress-strain curve is more accurate representation of the material's behavior during tensile testing, as it takes into account the deformation of the specimen's cross-sectional area and length. As we see in the graph, the true stress values are generally higher than the engineering stress values during the strain hardening phase. Also, the true fracturing point is significantly sooner than on the engineering stress-strain plot. This fact could be important in application because knowing the true fracturing point comes sooner can prevent unnecessary breaking of the material. So to summarize, in this presentation we covered first the engineering stress-strain relationship and significant points in the curve, including the plastic deformation region, yield stress, strain hardening region, ultimate stress, and necking region. We also calculated the Young's modulus, which is the slope of the initial linear portion of the stress-strain curve. Note that this value is similar whether we use the engineering or the true stress-strain relationship, because those two graphs only differ significantly when after the ultimate, because these two graphs only differ significantly after the initial linear region. The calculated value for Young's modulus is 74,179 megapascal for our specimen. Finally, we determined the true stress-strain relationship. Thank you for listening.